Unit 1.1 introduces us to measurements in physics, and it brings in some of the foundations of what we do in terms of problem solving in labs. I don't want to spend a ton of time on this, though, because we will learn this as we move throughout the year. The first thing is to understand that every measurement and every value that we talk about this year are going to be based off of what are called base units. These are 7 units that, when combined, form every other form of unit, but that is just time. We measure in seconds, distance, meters, mass, kilograms, and really those are the main 3 that we're going to focus for the first part of the year. Current, temperature, substance, and luminosity will be later, but we need to understand that all the other units are going to be some combination of these in the future. And while other classes might use, grams or centimeters or millimeters, in physics, we almost always convert our distances into meters, our masses into kilograms, and our times into second. From those base units, we are able to produce every other unit or derived units that we're going to use throughout the year. Some common ones that we can understand are speed or velocity, which we know as simply distance over time. And we've learned in the past that that is meters over seconds. Now, we are going to write that in IB as meters per second. We almost never will write things in a fraction, but we will use the exponent formation of the units as meters times seconds to the -1. To understand that, anything 4 to the -2 would be like writing 1 over 4 squared. That's the exact same thing, or 1 over 16. So when we write this as meters times seconds to the -1, that is the same as writing as meters over seconds. So you can see it's a combination of a distance and a time. Other ones you're familiar with probably are forces measured in newtons, which from our equation sheet, we're going to see F equals ma, which that is mass, which is in kilograms, and then acceleration, which is just right here, which we can see is a combination of distance and time. So that is kilograms times meters times seconds to the -2. So some of the units that are derived will have fancy names called newtons, or we'll just leave them as their base units combined. Such as momentum, there is no fancy way to say that, so it's just kilograms times meters times seconds to the -1. Whereas force, we can convert this kilograms times meters to seconds to the -2 into a unit called newtons. This can be very helpful when working through problems, is being able to work through these base units and how they build these derived units. And let's just focus on, lastly, this concept of energy. You've learned in the past of potential and kinetic energy, and both of those have different equations, from mgh to 1/2 mv squared. And while energy is measured in something called joules, both of these equations have to provide the same derived units. So mass is kilograms, gravity is acceleration, which is meters per second squared, times height, which is in meters. 1/2 mv squared would be kilograms times velocity, which is meters times meters per second, that value squared. And if we look at, both of these are actually going to come out to the same units of kilograms meters squared times seconds to the -2, and kilograms meters squared times seconds to the -2. So even though they are different equations, the units, when combined, can form the same derived units, which we simplify as just saying a joule. For all these units, we're going to use the metric prefixes to help us identify when values are larger or smaller significantly than simply the base. So in terms of those base units, whether they are the actual base units or the derived ones, if our values are significantly larger than our base, we're going to use these metric prefixes here, which are going to indicate values either 10 times or 100 or 1,000 times greater than my base. If they are smaller, we're going to use the metric prefixes that we find over here, which are going to indicate 1/10, 100th, 1,000th, right? Remember, 10 to the 1 is simply 10, 10 to the 2 is 100, 10 to the 3 is 1,000. Likewise, 10 to the negative 1 is simply 1/10, 10 to the negative 2 is 1/100th, and 10 to the negative 3 is 1/1000th. So these are going to be ways that we can indicate the size of something. So if we have 7,000 newtons, we could also write that as 7 kilonewtons. Or if we're talking about things that are very small, like the distance of an atom, per se, right? Here's the nucleus and the electron orbiting around it. We can talk about distances that are into the 10 to the negative 12th, all the way to 10 to the negative 15th meters. Okay, so that would be picometers all the way to femtometers. Okay, and that's how we're going to designate and really identify the size of things that are different from the base. And to help us with that, we're also going to use scientific notation to help us write out values, especially when values are incredibly large or incredibly small. And the format that we're going to use for that is if we were to have 7.35 watts, we would simply be able to write that as 7.35. That's times 10 to the 0 watts. Or if we were to have 73.5 watts, we would write that as 7.35 times 10 to the 1 watts. Whereas if we had 735 watts, we would write that as 7.35 times 10 to the 2 watts, okay? And so we'll see that we always want to have simply one value in front of our decimal point, and then all the other values behind that. This is going to make it easier for us, especially in both large and small numbers. When we get into small numbers, instead of having to write out so many decimal points here, we can simply, again, write it as 7.35 times 10, and I can simply count 1, 2, 3, 4, 5, 6, 7, and that's going to be times 10 to the negative 7 watts. The next concept we're going to look at is something just called sig figs, where this is the main definition of sig figs, and really how we're going to break this down is the first non-zero is the most significant. So for all of these, that most significant digit is going to be here. If there is no decimal point, the rightmost non-zero digit is the least significant. So for this one here is the last non-zero because there is no decimal point, and then everything in between is significant. Okay, so if we look at that, that's 1, 2, 3, 4. So this value here is going to have 4 sig figs. Okay, the one above it, if there is a decimal point, the rightmost digit, even if it is 0, is the least significant. So this is going to be my least significant digit right there. And so this then would have 5 sig figs. And then same thing here. Least significant, if I count through 1, 2, 3, 4, 5, 6, 7, 8, this is going to have 8 sig figs. Okay, so even though these numbers are very similar, the number of significant digits is going to differ. And really the number of sig figs is going to depend on the precision of our measurement. And we'll see some examples of that. Basically, the idea is if we have, a ruler that is just broken up into decimeters, so every 10 centimeters, that is not and we have, oopsie, that's a 30, and we have, something that's an awful color. We have something that is this long. We can't be very precise with this. We can say it's somewhere between 20 and 30, and so maybe our estimate would be, 24 centimeters, okay? We're definitely significant with 20. We know that for certain, but 4 is kind of a guess, right? And so that kind of shows us what our guess is, where we only have 2 significant figures. Whereas if we were to add, the centimeters in between here, okay, I could say, well, look, 21, 22, 23, 24, but it's somewhere between 24 and 25. So now I've given this, okay, now it's 24.3 centimeters. So I've just increased my precision by having a better measuring tool. And so from that, I have more significant digits. I know 20 and 4 for certain, but it's the 3 is kind of the guess. If I were to then, zoom in and get those millimeter lines here, okay, we could even then guess even more precise of 24.32. So the number of sig figs is going to depend upon how precise our measurements are. Now please understand that there are going to be times throughout the class where sig figs are going to play a factor and they're going to be important. There's also going to be moments where sig figs aren't going to be as important to us in terms of just our understanding. So we will try to break into when sig figs are going to play a larger role and when they are not. Lastly, then, we'll just finish with the idea of what is the rule of determining the number of sig figs for an answer when we multiply and divide those sig figs. So if we were to take a number of 2.4 and multiply that by 3, okay, what would we do there? So if we were to simply multiply it, we would have a value of 7.2. Now what we have to look at is this number here has 2 significant figures, whereas this number here is going to have 1. And for multiplication and division, including powers and most functions, the least number of significant figures in any of the operands often determines the number of sig figs in the result. So with that, this value of 7.2 needs to then just simply be written as 7 for my final answer. If we were to take 120 and multiply that by 2.00, we're going to look at this number and we would have a value of 240. Now, we could write it out like this because this has 2 decimal places, but let's look at our number of sig figs, okay? This value here is going to have 3 sig figs. The 120 is simply only going to have 2, and so I would need to then only write this value as 240. That is going to only have 2 sig figs. Now, if I were to do that one more time as 120.00 times 2.00, we still get 240.00. And now this has 5 sig figs, whereas this number has 3. And so my answer has to be written with 3 sig figs. So 240 point. That is going to be how I'm going to designate 3 sig figs. Simply by putting a decimal point here, that makes this 0 significant, even with no trailing numbers there. This is going to take some time to get used to. I'm not expecting us to be masters of it right off the bat, but just wanted to get us started with understanding some of the intricacies that we're going to need to deal with as we're working through problems this year. And again, with this, if we look, 7 is not very far from 7.2. So sometimes when we are just getting an answer, 7.2 is going to be fine. But if we need to actually provide it in a more precise way, 7 is going to be a better answer. Same thing with all of these. These obviously are all the same number, but they are just written very differently depending upon the number of sig figs that they are recorded with.